Good morning. It's March 18th, and this is your daily brief in science. Here's everything you need to know. Researchers at Pennsylvania State University have introduced a pioneering technology known as audible enclaves. This innovation enables targeted listeners to hear audio through intersecting ultrasonic beams, a method that could transform audio experiences in shared environments. The technique, outlined in a recent publication in the Proceedings of the National Academy of Sciences, utilizes two non-linear ultrasonic beams that converge at a specific point to create localized sound zones. By emitting two slightly different ultrasonic frequencies that are inaudible individually, the system allows sound to become perceptible only at their intersection, forming what the researchers call an acoustic capsule. Co-author Yun Jing highlighted that this technology effectively creates a sound barrier for private listening, as the interaction of the beams at their intersection produces audible sound. This advancement holds the potential to revolutionize audio experiences, enabling private conversations and personalized audio in public spaces. The system operates efficiently across a frequency range of 125 Hz to 4 kHz, making it suitable for various applications in environments like museums, offices, and vehicles. Testing has confirmed its effectiveness, with sound being audible only at the intersection of the beams, as demonstrated using a dummy equipped with microphones. However, challenges remain, particularly regarding sound quality and energy efficiency, which must be addressed before the technology can see widespread adoption. Future improvements may incorporate machine learning algorithms to enhance sound quality, with initial applications expected in vehicles. Notably, the ultrasonic beams can navigate around obstacles, ensuring functionality in crowded environments such as subways. Safety studies indicate that the ultrasonic beams operate well within FDA exposure limits, generating only a fraction of the threshold, although precautions are advised. The acoustic metasurfaces involved in this technology are created using advanced 3D printing, allowing for compact designs that are much smaller than traditional audio equipment. Researchers at the University of Rochester have made a groundbreaking discovery in the field of material science, revealing that twisting two atom-thin materials at high angles can unlock unique optical properties. This advancement could significantly impact quantum computing technologies. The focus of their study was on molybdenum diselenide, a complex two-dimensional material. By twisting it at angles up to 40 degrees, the researchers observed the formation of excitons that retain information when activated by light. PhD candidate Arnab Barman-Ray noted the surprising retention capability of molybdenum diselenide when compared to other Moire materials. This finding suggests that further exploration of different materials could lead to even better performance in quantum applications. Professor Nicholas Vamivakis, an expert in optical physics, explained that twisting these materials allows for optical control of artificial atoms while shielding them from environmental interference. The study, published in Nanoletters, demonstrates that layering these nano-thin materials creates excitons, which can function as qubits for quantum information processing. The researchers view their findings as a significant step toward developing new quantum devices, with potential applications in quantum networks and advanced lasers. This research was supported by the Air Force Office of Scientific Research and conducted at UR Nano facilities. This work builds on the foundation laid by the 2010 Nobel Prize-winning discovery of graphene, which exhibits special quantum characteristics when layered and twisted. The team believes that investigating other materials with higher information-retaining capacities at large angles could yield even better results, expanding the possibilities for future quantum technologies. Previous studies have primarily focused on small angle twists of materials to create moire superlattices, which exhibit properties like superconductivity. A new technique developed by Ritu Raman, a professor at MIT, is set to transform the field of robotics with the creation of artificial muscles that can generate force in multiple directions. This innovative approach, known as the stamping method, employs a 3D printed stamp with microscopic grooves to guide the growth of muscle fibers within a soft hydrogel. This method addresses the long-standing challenge of replicating the complex orientations found in natural muscle tissues. Traditional artificial muscles have been limited to pulling in one direction, But Raman's breakthrough allows for both concentric and radial contractions, significantly enhancing movement capabilities. This advancement is crucial for the development of biohybrid robots that are powered by lab-grown muscle, enabling them to navigate complex environments in ways that traditional machines cannot. Future applications of this technology could lead to the creation of soft robots that are energy-efficient, biodegradable, and capable of maneuvering through intricate surroundings. Raman's lab is focused on engineering biological materials that mimic the complexity of natural tissues, with potential uses in medicine and soft robotics, especially for restoring mobility in individuals with neuromuscular injuries. The research underscores the architectural complexity of natural muscles, which feature fibers arranged in various orientations. The stamping technique is versatile and can be executed using standard tabletop 3D printers, allowing for the creation of diverse tissue patterns. This versatility may extend its application to other biological tissues, including neurons and heart cells. The findings were published in the journal Biomaterials Science and involved collaboration with researchers from Tel Aviv University, with funding from various U.S. governmental organizations, including the Office of Naval Research and the National Institutes of Health. Notably, the researchers demonstrated their technique by creating an artificial muscle-powered structure that mimics the human iris, capable of contracting and dilating in multiple directions. Raman emphasized the potential of this technology to revolutionize robotics by enabling the creation of the first skeletal muscle-powered robots that can generate force in multiple directions. A recent review published in the journal Neuron has shed light on the long-term effects of childhood stress on brain development. Researchers from the University of California, Irvine, emphasized that over half of the world's children face early life adversity, significantly increasing their risk for cognitive and mental health issues later in life. The authors critique existing adverse childhood experience, or ACE, scoring systems, pointing out their limitations in predicting individual outcomes. They advocate for a more nuanced understanding of early life stress, highlighting that unpredictability in a child's environment is as critical as traditional adversities like abuse or neglect. A novel finding from this study indicates that unpredictable sensory inputs from caregivers can lead to adverse neurodevelopmental outcomes, even when controlling for traditional adverse childhood experiences. The research identifies key molecular mediators of early life stress, such as glucocorticoids and neuropeptides, which significantly influence affected neural circuits. At the molecular level, early life stress can alter gene expression through epigenetic changes, impacting how the brain responds to future experiences. Animal models used in the study have shown that different types of stress yield varying outcomes, influenced by factors like stress type, timing, species, and biological differences. In light of these findings, lead author Dr. Tali Z. Baram advocates for increased funding and research focus on early life adversity to improve mental health outcomes and reduce societal burdens. The authors propose redefining early life stress as early life adversity to encompass a broader range of impactful experiences affecting brain development. This comprehensive study has received support from multiple grants, including those from the National Institutes of Health and the Hewitt Foundation for Biomedical Research, with key areas for further investigation including stress perception in developing brains and identifying the ages most vulnerable to adversity. Recent research is reshaping our understanding of human evolution, suggesting that Homo sapiens may not have emerged from a single lineage in Africa as previously thought. Researchers from the University of Cambridge have discovered that modern humans likely resulted from a genetic mixing event between two ancient populations that diverged around 1.5 million years ago. This new perspective indicates that the evolutionary process is far more complex than a straightforward lineage. Approximately 300,000 years ago, one of these populations contributed 80% of the genetic makeup of modern humans, while the second population, contributing 20%, included genes related to brain function that may have played a crucial role in human evolution. Dr. Trevor Cousins, the study's first author, highlighted that certain genes from this lesser-known ancestral population significantly influenced the course of human evolution. After the divergence of these populations, one faced a severe bottleneck, potentially impacting the genetic contributions to modern humans and leading to the divergence of Neanderthals and Denisovans. Cousins emphasize that this research reveals a complicated ancestry, showcasing the separate development of human groups for over 1 million years before they eventually merged. The research team developed a computational algorithm named COBRA to model the splitting and merging of these ancient populations, utilizing data from the 1000 Genomes Project. Looking ahead, the team aims to refine their model to better reflect gradual genetic exchanges and to investigate early human diversity through fossil evidence. Supported by Wellcome, this study underscores the intricate tapestry of human history as revealed through modern DNA analysis, with potential candidates for these ancient ancestors including Homo erectus and Homo heidelbergensis. However, further research is necessary to align genetic data with fossil records. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.